All right, let's jump right in. Welcome to today's explainer, where we're going on a pretty fascinating journey into the invisible, heroic, computational hacks that make real-time 3D environments look so incredibly real. We don't often stop to think about how a digital simulation actually renders the world around us so seamlessly, but let me tell you, it takes a staggering amount of hidden engineering. Today, we're pulling back the curtain on one of the absolutely most complex mathematical magic tricks in all of computer graphics. We're talking about digital shadows.
So picture this. You're walking down a beautifully sunlit digital street. You step across a concrete plaza. The lighting is just perfect. But as you step forward, a sharp, highly visible seam sweeps across the pavement right in front of you. That beautifully smooth, high-resolution shadow cast by a tree, it instantaneously snaps into a blocky, pixelated staircase. Or maybe you wave your hand, and the soft shadow on the ground literally lags behind your movement by 2 full frames before awkwardly snapping into place. It's a glitch in the matrix. In technical terms, the universal depth rendering engine just suffered a shadow map cascading error.
Now you might be wondering, why on earth does this happen? Why do our digital shadows suddenly turn into these pixelated staircases, or lag behind us like some sort of delayed ghost? Well, it's not an optical illusion, it's not eye fatigue, and it is definitely not just a random bug. It is a fundamental limitation of the hardware desperately trying to keep up with the physics of light. Let's solve this mystery and figure out exactly what breaks when our digital worlds fail to cast a proper shadow. Because to understand the fix, we kind of need to understand the failure first. We're looking at a complete breakdown of what engineers call the dynamic shadow map pipeline.
All right, part 1, the shadow engine glitch.
When a system starts buckling under pressure, the symptoms are, well, pretty undeniable. We start seeing those crisp outlines shifting to blocky staircases. We get that totally unnatural 2-frame lag. You might even catch temporary black voids popping in behind closed doors as the system struggles with occlusion. What this all really boils down to is that your central host machine, your poor graphics card, which is probably physically sweating right now, has simply hit its absolute maximum video RAM throughput limits. It physically cannot render high-definition depth buffers for every single shadow across vast digital distances all at the exact same time. It's just too much data.
Which brings us to part 2, the cost of realism.
So, simulating harsh, hard shadows, piece of cake for a computer. But generating realistic, soft shadows, the ones with a dark center called the umbra and a fading, blurry edge called the penumbra, is an absolute mathematical nightmare. Just take a second and think about this number, 256. This is the ideal amount of point light samples required from a single area light source to calculate perfect, mathematically correct, ground truth soft shadows for a scene. To make a shadow look perfectly real, the computer basically has to pretend the light is coming from 256 slightly different angles and then average every single one of them out.
Honestly, this 256 number is just a one-way ticket to a GPU meltdown. Here's how standard shadow mapping works. First, the engine divides the light into those 256 samples. Second, it has to render a distinct 2D depth map for every single one of those samples. Third, it assesses the visibility between points for every single pixel on your screen. And finally, it merges all of them together. Now imagine asking your computer to do this entire process 60 times a second for every single shadow in a massive city. It creates a computational wall that brings even the absolute best hardware to a crawl. It's just not feasible for real-time rendering.
Okay, moving to part 3, cascading, the spatial hack. Since doing it perfectly is totally out of the question, we have to cheat. And engineers are arguably the best digital illusionists on the planet. To pull off this first major engineering hack, we need to understand the space we're playing in, the view frustum. Imagine a 3D cone extending straight out from your digital camera or your character's eyes. That cone is the view frustum. It's everything you can currently see. Think of the rendering engine as an artist with a very, very limited amount of highly detailed paint. If they try to paint the whole universe with that detail, they'll run out immediately. So they have to focus that detail only on what's directly in front of them.
Enter Cascaded Shadow Maps, or CSM for short. This is just a brilliant workaround. Instead of treating the whole view frustum equally, engineers literally chop it up along the depth axis, the z-axis. They slice it into segments. The slice closest to the camera, that gets the ultra-high-resolution shadow maps. The next slice gets medium resolution, and the slice way off in the distance gets incredibly low-resolution shadows. Because things are so far away, your eye literally can't tell the difference anyway, completely preventing the engine from wasting precious rendering resources on distant objects. This elegantly solves the perspective aliasing problem, those jagged edges, but only for things far away. What about the shadows right in front of us? Even with cascades giving us high resolution up close, if a shadow is undersampled, it's still going to look like a harsh, jagged staircase. We need a second hack to smooth things out.
Which leads us to part 4, filtering the jagged edges. That brings us to percentage closure filtering, or PCF. Instead of doing the incredibly heavy math to render a physically perfect soft shadow, PCF takes a bit of a shortcut. It essentially looks at the jagged edge of a hard shadow, compares the depth to the pixels right next to it, and just averages the results. It effectively blurs the jagged edges. You're trading a tiny bit of physical precision for a massive, massive increase in speed. It's pure digital sleight of hand. But let's look at how this used to work versus what we actually need today. Older hardware relied on a fixed 2x2 grid filter. Sure, it was fast, but it still left distinct aliasing patterns. It just looked rigid. Modern environments need wider blurring, but if you just force the hardware to use a massive fixed 7x7 filter everywhere, it drastically slows down compile times and eats up all your memory. We desperately need variable filter sizes that adapt dynamically, but pulling that off efficiently, incredibly tough.
And that brings us to the grand finale, part 5, the ultimate combo technique.
Okay, this is where it gets incredibly cool. What happens if you take the spatial genius of cascades, combine it with the blurring power of percentage closure filtering, and perfectly optimize them both? You get this brilliant 2023 academic breakthrough. They figured out how to split the view frustum into 3 distinct cascades, but they didn't just change the shadow map resolution. No, they tied the PCF blur kernel directly to the cascade distance. In that first cascade, right next to the camera, they map a heavy, beautiful 5x5 blur kernel to give you perfect soft edges. In the middle cascade, they drop it to a 3x3 kernel. And way off in the distant third cascade, where you can barely see the details anyway, they use a super cheap 2x2 kernel. They are literally dynamically scaling the math based on human perception.
But wait, it actually gets smarter. To control all of this, they use something called hardware occlusion queries, or HOQ. Essentially, the system constantly runs a rapid-fire test asking, can the player even see the artifacts if I stop calculating the light source here? If the answer is no, the HOQ immediately stops the system from subdividing the light source any further for those distant objects. It stops the math dead in its tracks, saving massive amounts of VRAM. You get pristine foregrounds and dirt-cheap backgrounds. Pure genius.
So what's the payoff for all this engineering gymnastics? It is massive. The standard methods take up a huge chunk of rendering time, but this 2023 multi-kernel technique, it yields a staggering 44 to 51% speed boost in frames per second compared to the old standard methods. They managed to perfectly simulate incredibly complex 256 sample soft shadows, but completely cut the rendering time in half without destroying your computer's frame rate or sacrificing visual quality where it actually matters to the human eye. So what's the big takeaway here? Next time you're wandering through some digital sunlit plaza, take a second to just look down at your shadow. If it's beautifully soft and smoothly follows your every single move, you aren't just looking at a dark spot on the ground. You are watching a real-time masterpiece of computational deception, spatial hacking, and dynamic filtering. It is invisible engineering at its absolute finest, which kind of makes you wonder, if the shadows on the ground are just an elaborate optical illusion, what other parts of our digital reality are entirely faked? Thanks so much for joining me on this explainer. I hope this sparked your curiosity, and we'll catch you on the next deep dive.